Yeah. I'm Andres, and I do VM work. I haven't been doing VM work for the last 7 years. When I started doing VM work, I came from doing whatever number of years in Smalltalk. I think at the time it was 12 or 11 or so. 11. And you change your point of view when you start doing VM work. And the VM I work with is written in C, and in a way it has to be written in C. And so, because I care a lot that the VM works and not just appear to work, but actually works, that desire is everywhere in what's going to follow. And so it really guides the decisions and things you see or things you look for, things you care for. So, but let's talk about what's really different from before. Your typical VM project. So the first thing I did at Syncom was to improve hashing. That took a few months or whatever. New symbol table, new hash functions, blah, blah, blah. And then came the first real project in this form. The problem was that we had 64-bit VMs and 64-bit images, but they didn't quite work. So basically we had some VM that appeared to work, and within a few seconds, kaboom, seg fault, or within a few seconds, kaboom, something doesn't work in the image, and followed by seg fault anyway. So go figure it out and fix it. And to some extent, when you receive projects like this, it's as if, just fix the couple seg faults, just fix the couple null pointer problems. But in reality, these kinds of things are more along the lines of, hey, do something about P equals MP, or sort of, and here's why. Well, I'm not going to go in chronological order because it's all a mesh of things that happen, but I'm going to tell you a few things of what 64-bit meant. So first off, there's a program called the image writer. It's a parcel or a package. And basically it can load a 32-bit image and spit out a 64-bit image equivalent. It can do other things too, but whatever. So if that's broken, well, from the get-go, you're not going to get an image that you can debug anyway, because you're not going to get the right classes in the right places. You're not going to get, objects written the right way. The image is going to be loaded, but the VM loader is going to think that object spaces are any which place, so things are not going to work. Seg fault, seg fault, seg fault. Weird behavior, strange things. So, okay, well, let's fix that. Well, hey, that means that now you must understand image format. Oh, you didn't know about image format. Oh, well, okay. Next thing, guess what? You can't load code from your code repository because you don't have 64-bit library support for your database. But even if you do, there's a lot of things like, everybody knows that an int, a 32-bit int, is always the size of a pointer. So when they read things and they put things in an FFI, instead of writing pointer to something, they write int or D word. And, things don't work anymore. But since the result is a crash or some such, it's a VM bug, so you get to debug all that. Well, let's say you fix that. Guess what? You can't load parcels from disk either. Why? Well, because parcels, they have a specific format for 32 bits, and if you load that into a 64-bit image, then you're starting to violate assumptions left and right. So, for instance, things are not of the right class. So, for instance, the Syncom's, the VM has immediate doubles. Those are not converted. A small integer grows, so now you have large integers that are not the right size, etc. Then it causes even more problems because there was. So, mind you, fix this means go understand how the serializer works. Rewrite it so you can actually understand it, and then subclass it, and hopefully you don't write too much code to make a 64-bit version of the same. And then realize that, no, you don't want to do that, so actually write another variant that works in 64-bit by pretending it's a 32-bit loader working properly. So, whatever. Then you find out that, hey, small integer change size. You think, oh, great, things go faster. Yeah, they crash faster too. So there's a specific type of compile method, and if how did it go? If the last literal is a small integer, then there's no bytecodes, and when that happens, then the last literal is actually encoding bytecodes, and there's some other tricks that you can do, whatever. So what happens when you have a 32-bit compile method in which the last literal is a large integer, but when you fix the serializer, then you load that compile method into a 64-bit image, the large integer becomes a small integer, now your compile method appears to be optimized, and you're running random bytecodes, and things don't work anymore. Guess what? Now you have to go fix the compiler. And every other file you generated, because they won't load, right? Or if you don't do that, now you have to go to the code management, and every time I see one of these methods, I have to recompile, well. Oh, by the way, comparisons in small integer were broken too, so 0 was greater than 2 to the 31 minus 1, or whatever the number was. So, 0 was greater than 2 to the 28 minus 1. So that's not going to work either. So you have to go fix that. Fix that means you have to go to the jitter and figure out what the encoding for the instructions are. And that's when you realize that the x86 code generator is not written in a way that resembles the Intel manual. So now you're talking about rewriting the code generator for that, and then fixing the problem and fixing the other things that you find in the process. Intel manuals for x86, 20,000 pages. The relevant ones for this work, about 5,000. Oh, guess what? Small doubles, right? Those are also broken. They don't work anymore. Haha. So you have to go fix that too. That means jitter. That means, whatever. Just the lot. Because of course you write tests for all this. So the more tests you write, the more problems you find. Guess what? Floating point, huh? There's C99 introduced the notion of pointer aliasing, in which the compiler always assumes that if you have a pointer that is of a particular type, say a pointer to a double, any other pointer that is of a different type is going to be pointing to a different address. In other words, you're not going to be using implicit unions. Because then the compiler can say, since the pointers are of different type, they are of different addresses, they are different things, so I can optimize scheduling, etc. Well, that means then that if you write something like star, parentheses, double star, parentheses, pointer to 64-bit integer, it all breaks. And it's not a compiler bug, it's your own source code bug. So now that means, guess what? You have to go read C99. 700 pages for you, thank you. Never mind compiler manuals. That's also when you find that, as I mentioned in talk in 2009, that primitive returns were misaligned. So, primitive methods have two addresses. One returns, the other one restarts the primitive, because some primitives restart, like semaphore wait, and some primitives return, like GC. But if those are misaligned, then in some cases you can restart when you mean to return, so you get into infinite recursions unless it's kind of buggy, so it works sometimes, and sometimes don't. And then it appears to work, but doesn't really. So go figure that out. Guess what? There's polymorphic inline caches, and this is a spectacular bug. I tell you, it's awesome. So here you have a polymorphic inline cache, and how did it go now? Oh yeah. The first class that gets compared gets loaded in the link send site, because it's an optimized, right? And all the others is, well, just compare a constant to the class of the receiver that you just loaded. So when the pick runs through and there's no match, then it goes to the VM, runs some C code, extends the pick, and jumps to the pick again, without voiding our class, which supposedly have been loaded in the link send site. Well, everything's fine as long as that register isn't touched by C or is written by some garbage, with some garbage by C, because you're violating the ABI because you didn't care. So it could happen that there is this variable for a Boolean in the C function, and that variable gets assigned the register of our class in the pick. And that variable could be, say, for when picks are an MNU pick, the pick that has a case for message not understood, and that the first case of the pick is for, say, array. But the first comparison is for an immediate case, or something like that. Yeah, it went like this. So basically, it ended up jumping on an immediate as if it was a non-immediate object, and now you're in La La Land and trying to read trying to read an immediate character as if it was a pointer, trying to get a class, kaboom, etc. Guess what? Now you need to go to study all that mess. C compilers were also problems. Say GCC. It's in the manual. It can read bit fields with instructions that are outside the bit field. So if you have an object header right next to a boundary where you malloc memory, you try to read and it seg faults sometimes when it tries to read the identity hash, and it only depends on whether the compiler decided to use those instructions or not. And of course, the GC was broken. So this meant 64 bits, right? So this notion that you can encapsulate VM problems in some nice sentence that, oh, do something about 64 bits. I mean, I'm not blaming Alan for it because he didn't know, we didn't know. But this notion that you can describe VM problems in nicely, encapsulated nouns or terms, I don't see how. By the way, that took 22 months. Speaking of GC, I said it was broken. Well, GC was supposed to be easy, right? That's David Bacon over there, and in 2004 he wrote an awesome paper in which he describes that basically every type of GC algorithm is the dual of the other, because there's basically two. There's reference counting, which is very good when there's little garbage, or tracing, also known as mark and sweep and other names, which is very good when there's a lot of garbage, because of how much memory they pull and how much work they do compared to the amount of garbage there is. So he says, well, great, every good GC algorithm is a hybrid of those two. Well, let's see why. Mind you, these are two algorithms that are extremely easy to describe. Mark and sweep, you can imagine, oh, you have a mark stack and you mark, and obviously you finish because sooner or later by induction, blah, 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 blah. Yeah, okay, very nice. So Visual works very quickly. You have a generational scavenger over there. But of course, if you want to find out what's not garbage there, now you have to scan old and perm, but that's a lot. So you do reference table, also known as reference counting, even though you're tracing inside new space from that. So here's the hybridicity. If you run a normal GC that pretends that perm space is not garbage, well, now you need to find all the references from perm to old or new, or at least you could find the references from perm to old. To save time, guess what? You have old remember table, more reference counting, even to speed up a tracing algorithm. Of course, then you have the incremental garbage collector, in which you can collect garbage in old incrementally. Like you do a little bit, you stop. You do a little bit of tracing, you stop. You do a little bit of tracing, you stop. Where do you hold the list for that? The mark list, the list of ephemerons, the list of weak objects? Well, you put them in old space. Where else? As byte arrays, right? So the image doesn't know what they are, but they are there. So now you start having problems. So let's say the IHGC is running, but it doesn't mark anything in new space because most objects here are young, so why bother? So instead, objects that get forwarded into old space while the INGC is running inherit the mark bit from the remember table, because if you have an object that was marked in the remember table by the incremental GC and you are tenuring something because you found it from there, then you also mark on tenure. So let me see, what happens exactly when you have a weak object over there and you tell it, oh, now become an ephemeron, and you change that, and then you mess with that some more and say, oh, now you change to a new class that I just created here. It's really complicated. The details kill you. It's not the algorithms that are, complicated. The algorithms are easy. The problem is the detail, the level of interaction, all the things that could go wrong, and all the things that you want to offer the people that use your software so they can write things that go quickly. Then there's the class table. So in 64 bits, objects don't reference a class via the class pointer. Rather, they have an index to a class table that is held in old or perm. And the class table then references the class. Of course, you want the class table to be weak, because then when you garbage collect, if no object references the class, then the reference goes away from here. You don't have to clean it by hand. That's awesome. Except, of course, what happens when you have a new class and all these instances are over there. Well, right, you won't find the class from here because you won't put those objects in the remember table anymore because they don't reference. So you put the class table in the remember table, but the class table is weak. So you find no strong references. What do? You throw the classes away? No, you can't. So now you have to treat the class table, which is weak, as if it were strong during a scavenge if the IGC is running. Yes?
You said you have the class table in 64-bit, not in 32 bits?
Not in that implementation.
Okay.
In 32 bits, it's a direct pointer.
Why is that?
Without going into too much detail, the official explanation is it makes all the object headers smaller, use less memory, and also some generated code also has to compare effectively 32-bit literals as opposed to 64-bit literals. So your generated code is smaller. So, again, the complications kill you. And, you know, so here's the thing. Even if you have a problem, like, oh, there's a bug with the GC somewhere, now you're talking about, hey, go understand all that. The scope of problems is much larger, way larger. And any detail is terrible. You miss one of those and the whole thing breaks. We had other sources of that. Yes?
Sorry, do you check for the class ID in the polymorphic line cache or for
the class tag?
Class tag, okay.
The class tag, which is the index in the class table and so on.
The method dictionary, right? Okay. Do you support instance method? No.
I didn't mean to refer to that, but we can talk about that later. So, these are all the sources of issues, well, at least some sources of issues that could come from things that you program in the VM. Oh, do something about 64 bits, deal with the brokenness in the GC. And already we're talking about huge things that take years to understand and get your head around so you can actually do something meaningful with. Then there's the other problem. That's Peter Hatch. That's a coworker of mine. I really like working with him. And back when I joined Syncom 7 years ago, not only we had that kind of problems on the VM, but also had problems because of C issues, just C alone. And it got so bad that he basically said, what is there? Things get so bad and things get so unstable that you cannot work anymore. Because as I explained, those problems that I was describing before, they need, in order to be resolved, to spend enough time. They need you to spend enough time to really understand it and concentrate and get down to all the details. And if you're constantly interrupted by, oh my God, segfault, oh my God this, oh my God that, you can't do anything because you're swapping in and out the knowledge all the time, and that's a very costly operation. So, what kind of stuff was preventing us from doing work? Well, back in the day, that was great. Very low complexity, you design your own hardware, you design your own VM, you write an assembler, great. You don't depend on anyone else, basically, and your whole image is 2 megabytes and awesome. Not anymore. Because these days, show me a laptop with an operating system not written in C. Okay, show me a mainstream laptop with an operating system not written in C. It's one way or another. And that's the issue. Just as you as or me even back in the day as a small talker would like to avoid all this complexity and have been told many times, oh, we have the VM for that, the VM hides all this complexity for you, and etc. As soon as you want to use something from this level, you pull in everything. You just don't pull the little bit you want. You pull everything, the whole context, the whole issue of understanding the whole VM, etc., the relationships between all the pieces, everything. And what happens? Well, I didn't get exposed to it when I started. So I was kind of blind to it. So what was I not seeing? Well, I was not looking at much as C, for example. So compilers, SDKs, what's that? Well, that's an issue because if you don't get... See, the thing I feel now is that I look at things written in C more from a C point of view than a Smalltalk point of view. And then I see, hey, you know what? They are dealing with the same problems we are dealing with. Only they write about it in a different language, but they try just as hard to implement a proper API, to decide whether to pass arguments one way or another, the way in which they will report errors, how they encapsulate implementation details so they don't leak everywhere. That is super important, because then you can let the compiler do the work for you. But if you're not aware of it, well, let's copy-paste all the stuff from the .h file, right? And in retrospect, I can see how doing that to a C program and importing that in the image, it would be a problem. Well, what kind of problems? Well, for example, since the VM is invisible and we never think about it, we typically ignore the implementation of the primitives. Or that typically happens, and that is a danger. A danger that is exemplified in this slide, because, for example, you could look at, say, some C libraries or whatever and say, oh, look, how nice, a timer interface. Let's call that the one you want to use, the C event T interface. And so you see, right, look, the document says that there's two, alarm mechanisms or timer mechanisms, and you can use one or the other, but not two at the same time. Well, I only use one, C event T, so that's fine. And if you don't look at the primitives, you realize that, hey, the VM is using the other one, oops, undefined behavior, and segfault, because you didn't look at the VM. And again, right, we've all been told, oh, you don't look at the VM, that has complexity for us. It's limiting, it's dangerous. In the same way, what about, oh, well, I just look at .h files and whatever the documentation says there is, I'm just going to use. Well, it's the same kind of problem. Let's pull stuff out of the .h files. Well, maybe the specification for that said you're not supposed to know what they are, because when we change it, if you don't know what they are, then encapsulation is not broken, and then your program is portable and keeps working even if we change stuff. Well, if you inline all the stuff from the .h files, you can't. And some Windows interfaces are like this. You're supposed to not know what the struct is or what members it has or anything. You're supposed to use functions to dereference it, and to you it's just an opaque blob of stuff. And we also tend to ignore, and this is something I did too, right? I was completely ignorant, and this is why it was shocking to me, that you cannot ignore how an FFI works. And for instance, there are many obvious APIs for operating systems that will insist, look, there is something called malloc, but it could be a function or it could be a macro, and you are not supposed to know one or the other. Well, if you're not supposed to know, that means that you cannot call malloc with an FFI, because you don't know if you're skipping the macro. And actually, on AIX, there is no malloc function. There's no such thing. So if you try to look up malloc, it's not there. And similar things happen, say, with stat on Linux and many others. So it is an issue. And all these things have standards and documents, etc. And it's a pile of paper, huge pile of paper. It's there because you're not supposed to know how it's implemented. But if you also don't look at that and don't become kind of a lawyer, I'm not saying that's fun, but because I care that the thing works, if I don't look at it, guess what? Bang! And now that becomes an emergency that prevents me from working on everything else. That's the issue. Not that I want to be a lawyer of C. God forbid MSDN, I don't want to see it. It's not like I have fun reading MSDN. It tends to be kind of vague. I understand their situation, that, well, they are in the boat they are. But working with it is hard because it's ambiguous. There's all these nitty-gritty details that you don't see. And the same thing with here, right? One little mistake, bang, segfault. So what did we do? We said, well, look, okay, we can't keep working like this. We can't keep piling on features. We need to get rid of stuff that gets in our way. Code that is half broken. A lot of C code that is half broken. Because one of the things that happens is that, because you don't like the segfault, then basically you end up, it's so easy to do. Mind you, it's so easy to do. It's not like you did it on purpose. But you end up changing code in a way that makes the problem go away, or appear to go away. You think you fixed it when you didn't, and now you have something that is, kind of wound too hard, and now you have here something else that depends on this brokenness, and now this gets wound too hard too. And now you get something else here that depends on the brokenness of the other two and the interaction. And that gets also wound too hard. One little change somewhere, bang, everything blows up. And then you think, oh my God, what happened? What I changed here that had nothing to do broke this. Oh, must be a compiler bug. I mean, it's so easy, right? It's so easy to go from one to the other. And no. I'm not saying it's fun to debug these things, but it's really important. So what did we do about this? And how successful were we? Right. I mean, you have all the requests for features, and you can do anything when that's what you get on the other side. Segfault. That means interruption, no concentration, nothing else. So this is a graph that I wanted to do for a long time. Now I put it in a slide. It shows the number of lines of code for the various versions of the VisualWorks VM, the HPS. And I changed syncom at about there where the color changed. And that's where basically Pete and I started this. I mean, Pete and I did most of the work. I mean, there were others, but I think, we did all that work non-stop for 7 years. And what happened was we went from 360,000 lines of code to about 240,000. And we added features to the VM. So that means that we're not reading a third of the code that used to be there. It doesn't come up. It's not there. It can't be wrong either. So mind you, this that happened here has never happened in the history of HPS that I can recall, that I can get my hands on, because the first source code I found was from 1990. And we have as much code now as, 15, 20 years ago? And there has never been a period of time in which for 7 years the VM source code base has gone down with every release. Well, right, but who cares? Well, this matters, because here we can see, we call our tickets ARs, so we can see the number of ARs done for each release as time goes by. And the red bars are how much the code changed in size, up or down, until 7 years ago, until here. And then you can see deletion, a lot of work. A lot of deletion, more work, deletion, more work, deletion, more work. So you actually get more stuff done if you get rid of these issues. It's a pain, I'm not saying it's fun, but you actually make more progress because you start getting less interrupted and now you can do more stuff. Now, speaking of GC, since that's something that I spent a long time on and I'm running out of time, or I'm close to running out of time, but not quite. By the way, I wrote 10,000 tests, and by hand I wrote them myself, and they ran with every build, 0 defects, failures, etc., the usual. So, this is my old slide of GC speed improvements from 2010. Basically, the red ones, they don't have all the bars, because the red ones is the previous version that crashed and didn't even finish, and so basically, to make the long story short, they used to take, if they had finished, that set of tests would have taken over a day, and when I was done with it, they were running in 73 minutes. But now I have a new slide, the 2013 GC improvement, where that happened. The last GC we shipped out is about 45% faster than the one that was faster a day to 73 minutes. And that's specifically because we delete code. We get rid of this intellectual burden that prevents you from working. That is super important. A lot of what I heard today in many of the talks reflect, or I recognize and I see those things, those values that were expressed is very familiar. Toddler's talk, for instance, about no shortcuts, production code or nothing. Because if not, segfault. Or, sorry, I'm running out of time. Huh?
Documentation.
Yes, the whole lot. It's super important. So at this point, I end my talk, and this is questions. And I didn't run out. Questions? Are we sleepy?
No.
Yes.
First question. So it's you alone, or how many people work on all these years?
all this cleanup and the stuff that I talked about, mostly Peter Hatch and myself. And Peter dealt with those issues for a very, very long time before I joined, and I think the difference between before and after is brutal. We like working much more on the VM now than we did 7 years ago because of all the false positives you would have to do, all the archaeology issues that you would have to run into, go study how this was broken in 1990 to figure out why it's broken today, etc. There are others, but I think that's where most credit should go. Yes?
I have a question. What's your opinion about backwards compatibility? And I'll give you an example. Let's say there's a stupid bytecode somewhere which you want to get rid of because it gives really headaches inside the VM. But which means that basically every image out in the world you have to recompile because before running on the new machine. But this will have a lot of advantages, but also some headaches for the customer. What's the concept in your personal opinion?
The stance that we've had, that this project, the HPS thing, has had for as much as I've been able to find in documentation, and that's 25, whatever number of years, is that within minor releases, so for instance, VisualWorks 7 blah, all the blah versions are minor versions. Within minor versions, we maintain backwards compatibility. Every so often, there's enough change, enough pressure is like the one you say, or enough need to go delete stuff that we left there for backwards compatibility that's getting in the way. I'll give an example. The fact that our VM, or Windows VM, is compiled, is both ANSI and Unicode. It's kind of schizophrenic right now. So it would be nice to get rid of the ANSI part because that's deletion of a whole lot of stuff, but we can't do it because of backwards compatibility. And when we go through a major release, at that point, we allow ourselves to break backwards compatibility from a VM point of view. So within minor versions, the deal is that any VM will run any image that is older than it. So for instance, a 710 VM will run a 7.7 image. That's how I could do the test, this thing. What's that, sorry?
Will it be able to read 1.0 image? How long do we go back?
No, within a major release cycle. So for instance, any 710 VM should be able to run modulo some small breakages that must have been or could have been exceptional, any 7.x image, but not a 5.x. Any others? Mind you, we are in a major release cycle, so I'm deleting code. This is awesome. Just delete, bye. Yes?
Control-A, Control-X.
Huh?
Control-A, select everything. Control-X.
Yeah, well, in some cases, yes, actually. Yes. Actually, yes. Recently, I integrated one of the changes that made this thing. I don't know if it shows, but you see that this one is slightly lower than this one. Those are deletions, and one of them was a whole new implementation, custom implementation of looking up symbols in a DLL instead of using POSIX DLSIM, DLOpen. Why? It's just delete. Okay. I'm past time. Any other questions? And if not, you can talk to me later. And if not, thank you.